All right, we're back, and I've got a picture of a pumpkin on the screen. So that made me think of how you repair a broken pumpkin with a pumpkin patch. Didn't like that one? Okay. What do you call a chubby pumpkin? A plumpkin. Nope. Okay. Well, anyway, I have a picture of a pumpkin here because we're actually going to watch a pumpkin get thrown.
Can I get a horn?
Steve Seegers is on the cusp of a new world record. Can Yankee Siege complete rival Matt DiFrancesco's challenge and hurl a 1,000-pound pumpkin?
Okay.
Will Steve's machine be up to the task?
3, 2, 1.
Cool. That was awesome. All right, so what does this flying pumpkin have to do with our quadratic graphs and quadratic equations that we've been working on? Well, when that pumpkin went flying through the air, it was an example of what is called a vertical motion model, which is a quadratic equation that models the height of an object depending on how long it's been in flight. So the equation for a vertical motion model is h of t. Now h of t is the same as f of x. The only difference is it's specifically telling us that our output or our y value is the height of the pumpkin at the specific time, or the height of whatever object it is we're looking at. So the height as a function of time is equal to negative 16t squared plus v sub 0 t, or v naught t, plus h sub 0, or h naught. Now this might look a little confusing, but it's really nothing too complicated. So in this equation, the y, which is our h of t, represents the height. The t, as you can imagine, represents the time in seconds, so how long the object has been in flight. V sub 0 represents the initial velocity, or initial vertical velocity, so the speed going upward of the object in feet per second. And then the h sub 0 is simply the initial height of the object. So at what point or at what height did it get released from, or shot from, or depending on, thrown from, depending on the different things we're talking about. What characteristics of the pumpkin situation indicate that it could be modeled by a quadratic function? Well, if you think about it, you had that trebuchet, or that big launcher thing, and when it launched the pumpkin flew up and then down. What shape is that? That is a parabola. Why does it form a parabola? Well, anything you throw up must come down, right? It's because of gravity, and gravity has a quadratic force attached to it. It's pretty cool. So if we suppose that a catapult hurls a pumpkin from a height of 68 feet, right? They had the machine, but it actually let go 60 feet above ground. And at that point, 68 feet above ground, the vertical velocity was 128 feet per second. Could we now take this information and plug it into a vertical motion model? Well, yes, of course. We know that the start of the vertical motion model is always negative 16t squared, and that has to do with the force of gravity. And then it was plus v sub 0 t. Well, v sub 0 was our initial velocity. It tells us that the initial velocity was 128 feet per second. So we get 128 t. So our b value essentially is our vertical velocity. And then at the end was h sub 0, which just meant our initial height. Well, how high was the pumpkin when it actually got flung into the air? Well, this tells us it was 68 feet above ground. So our h sub 0 is an initial height of 68. So this quadratic function will actually model the flight of the pumpkin. Does the function you wrote have a minimum or maximum? Well, our a value is negative. If our a value is negative, that means our graph is going to open downward. And if our graph opens downward, we're going to have a maximum. And how can we tell that from this form? Well, we know it's a maximum because the a is a negative. Okay, I went ahead and graphed that equation for the pumpkin chunkin. So here's a graph of the pumpkin. And we're asked to label the axes. Well, we know that the function was h of t, right? And what did h of t stand for? Well, it stood for height as a function of time. So it meant that the height was dependent, which is always the y-axis. And we know we were measuring the height in feet. And it depended on the time. So the time is going to be my x-axis. And we're doing time in seconds. So when we're doing problems in context, word problems, we always want to make sure that we know what our labels for our x-axis and our y-axis will be. Oftentimes they'll already be there for you, and it's just important to make sure as we answer questions, we refer back to our labels, because that's going to help us interpret the problem. This says, what is the max or min? Well, we know it's a maximum, and we know it's this point right here, which is the ordered pair 3.75, comma 393. So that's easy to be able to look on a graph, find that vertex, read what it says, right? The more important part as we get into context is, what does that actually mean in the problem situation? Well, it's pretty simple. This is my x value. What does my x represent? Well, x represents time, and it's time in seconds. So this is our time in seconds. And then my y-coordinate goes with my y-axis, which was representing the height in feet. So I know this is representing the feet in the air. And then the other part is, it's our max, right? So this pumpkin went flying through the air, and eventually, at some point, it started to come back down. When it's at its highest point, that's called the maximum, right? That is the highest that the pumpkin went. So the highest that the pumpkin went was 393 feet. Well, how long did it take to get there? It took 3.75 seconds from the time that it was launched. So I don't have a whole lot of room. I'll try to squeeze that in there. But our vertex essentially means the max height the pumpkin reached was, and it tells us right here because this is our vertex, which is our maximum. So the max height that it reached was 393 feet. And it reached that in 3.75 seconds. So the maximum of this graph tells us that in 3.75 seconds, the pumpkin reached the maximum height of 393 feet. All right, next question, interpreting the graph. What is the y-intercept? Well, the y-intercept was 0,168. And explaining what it means in terms of the problem situation, we basically do the same thing. We know that 0 is our time, so that's 0 seconds. We know 168 is our height, which is in feet, and I think I just realized that I accidentally put 168 instead of 68. So forgive me, these answers are not the one to the equation we wrote on the last page, but I put in 168, so we're going to roll with it. If my y-intercept is 0, 168, that means that at a time of 0 seconds, the height was 168 feet. Or at the beginning, so at the start, the pumpkin was 168 feet above the ground. All right, last question on this page. When does the catapulted pumpkin hit the ground? Well, what does the ground have to do with either the time or the height? Well, the height of the ground should be what height? If the pumpkin started at 168 feet and it reached a maximum height of 393 feet, what would be the height when it hit the ground? The height of the ground is 0, right? There's 0 feet above ground is the ground. So we can look on our graph and we can look simply to see where did this pumpkin hit the ground? Where did it reach a height of 0? Well, it reached a height of 0 when the time was 8.706. So we'll call that 8.7 seconds. And how did we determine that? We looked to see when the height was 0. Now, you might be thinking, what about this height over here? Right here, the height's 0. Does that mean it was on the ground? Well, not really. And that's where we get into the fact that when we do problems in context, when we do word problems, sometimes some of the points on the graph don't make sense. Because I can't go back in time to negative 1.206 seconds. So this ordered pair, and to be quite frank, anything left of 0 does not work for the problem. It's not going to actually be a part of our problem. All right, another example of where we can use a vertical motion model is with a model rocket. And again, something else that flies up, comes down, right? Anything that goes up and comes down can be used, modeled with a vertical motion model. So again, why does it make sense that this is modeled with a quadratic function? Well, it goes up, and then it comes down, right? Goes up, then down. So it's going to be vertical motion. Write a function. Now it says g of t. I don't know why they use g, but we'll go ahead and use g because they wanted to. To describe the height of a model rocket in terms of t, it has an initial velocity of 160 feet per second, and it is launched from the ground. So I know that it's always negative 16 t squared, but then it's plus the initial velocity, so plus 160. And then that always has a t attached to it. And then the initial height goes last. Well, if it's launched from the ground, what's the height of the ground? 0. So do I need to put plus 0? No, I'm good. I'm just going to leave it like that. The independent and dependent quantities, well, it's g of t. This is always your dependent. This is your independent. And we know that t is going to represent time. So that's time in seconds. So my independent is time in seconds. And then just like the pumpkin, our output, our g of t, is going to be the height that it reached, which we're measuring in feet. Right? So our dependent quantity is height. And once again, we're measuring that in feet. So what I went ahead and did was I graphed this, and we're going to label the axes. So again, we know we have time in seconds, and then height in feet. And so we're looking at how high in the air this rocket is, depending on how long it's been since it was launched. The maximum height of the model rocket, well, we have to go to the max, right? If we're finding a maximum, we go to the maximum. The maximum is right here at 5,400. Okay, and so we know that the maximum height, is that going to be the 5 or the 400? Well, 5 is our x, that is our time, but y is our height, right? So 400 feet is the maximum height. And then the second question is, when is the rocket at its maximum height? So that's saying at what time, right? So if I go to this, the time is my x. So the time is at 5 seconds. So we know that it takes 5 seconds for this model rocket to reach its maximum height, which is a maximum height of 400 feet. All right, determine the x-intercepts, then interpret the meanings. So our x-intercepts are at 0, 0, and 10, 0. 0, 0, and 10, 0. And again, if you ever get stuck on an interpreting question, just go back to what is the x representing, what is the y representing. So x is representing time in seconds, right? And the y is representing your height in feet. So my first x-intercept, or my first zero or root or solution, is 0, 0, which means at a time of 0 seconds, the rocket was at 0 feet. So 0 seconds is the time that it's going to get launched, and at that time the rocket was at a height of 0, which means it is on the ground. Well, the next time it got to a height of 0, right, to our x-intercept, was at 10 seconds. So at 10 seconds, our height was once again 0 feet. So these 2 points represent the times at which the rocket is on the ground. Or we might even be more specific, because we know that once it hits the ground, it's actually going to stay on the ground, right? So it's going to be on the ground probably at 15 seconds too, not just at 10. But we could also think about it as the time the rocket got launched and when it hit the ground. So we know that at 0 seconds and at 10 seconds, the rocket was at a height of 0, so it was on the ground when it got launched and when it landed. Continuing with the model rocket, we're going to talk about the domain and range again. The domain and range in context of a problem is going to be different, usually, than the domain and range of the function. So we know that the domain of the function is always all real numbers, right? We can plug in any number for x and get a solution. But in context, not every number is going to make sense. So when I think about the domain, I'm thinking about my x values. So I know that my domain is going to be my x, or in this case, time. And if I just looked at the graph would keep going forever left and right, and my domain would be all real numbers. But in context of the problem, are we going to go back in time? No, we're not going to look at negative time. Also, the rocket hits the ground at 10 seconds. At that point, the flight is over. So I don't really care what happens after 10 seconds because the rocket has already completed its flight. So the only x values that we're actually looking at when we're looking at the flight of the rocket are everything from 0 until we get to where it hits the ground at 10 seconds. So in context of the problem, we're only looking at the domain from 0 to 10. In context of the problem, we're only looking at the flight from 0 seconds to 10 seconds. Anything beyond 10 seconds, I don't care. The rocket already hit the ground. It's pointless. We're just looking at those 10 seconds. So in context of the situation, the domain is 0 to 10. Likewise, with the range, we do know that the range in general, if we were just looking at the graph, the range would be y is less than or equal to 400. But in context of the problem, we have to think about what heights, right, because range is our y and height is y, which heights actually make sense for the rocket to be at? Well, yeah, the rocket did reach 400 feet. We know that. But what's the lowest that the rocket went? Did the rocket go negative 7,000 feet underground? No. the lowest that the rocket goes is 0 feet. It doesn't go below 0. So it's at 0 feet, right? Now it's at 200 feet. Now it's at the max of 400 feet. It's coming back down. It's at 300, it's at 200, it's at 100, and then it hits the ground at 0. It doesn't keep going. So although the range of the function is anything below or equal to 400, in context of the problem, the range is not just, it's not just anything below 400, it's anything from 0 to 400. So if I put y is less than or equal to 400, that would include negatives, but if I specifically write it as 0 to 400, that means that the height that the rocket reached was anywhere between 0 feet and 400 feet. Next question, how is the range of the quadratic function related to its absolute maximum or minimum? Well, we know that the range value, right, the 400, is always the y-coordinate of the vertex. So anytime you're finding the range, find the y-coordinate of your vertex, and that will be included in your range. So y-coordinate, coordinate of the vertex is always a part of the range. And not just any part of the range, but it's the actual maximum or minimum of the range. So it'll always be one of the numbers that we plug in. All right, use interval notation to describe the interval for which the rocket is increasing and decreasing. So again, the interval of increase is where it's going up. And we're gonna look in context because, again, we said we're not gonna look at negative time. So at a time of 0, the rocket is going up, it is increasing. At what time does it no longer increase? Well, when it hits here, which has a time of 5 seconds. So I know the rocket is increasing from a time of 0 until a time of 5 seconds. Once it reaches 5 seconds, the model rocket is going to go down until when? Well, it's going to go down until it hits the ground, which was at a time of 10 seconds. So it's decreasing from the time of 5 to 10. All right, one last example. We're going to look at a couple questions. Again, the main goal from looking at a vertical motion model is more so about reading the graph and interpreting the graph than anything else, at least in IM2. So now we're going to look at a coconut that is falling from a palm tree. So it's already up on the tree and it breaks off and it falls down. It says that it began 25 feet above the ground and it can be modeled by this function. Now you might notice there's no b value. Well, the b is the velocity, and if it just breaks off, it has no velocity to start. It gains velocity as it goes down due to gravity, but that's why there's no b value. But if we label the axes, we're looking at the height of the coconut. So once again, we're always looking at height and time. And this one again is going to be feet and seconds. So the height in feet and the time in seconds. After how many seconds does a coconut hit the ground? Well, we go to where the coconut hits the ground, which is at the x-intercept at a height of 0. So when it reached a height of 0, how long did that take? Well, an x value of 1.25 represents the time of 1.25. So it took 1.25 seconds. How did we know? We looked to where the height was 0. And why didn't we look over at this height? Because that's going back in time and it doesn't make sense. In context of this problem, anything left of 0 doesn't make sense. The zeros of the function, which is actually what we just talked about, they are negative 1.250 and 1.250, right? There are x-intercepts. But we said negative time doesn't make sense. So I'm going to say does not make sense in context of this problem. We can't go back in time. And even if we did go back in time 1.25 seconds, it wasn't on the ground. It was actually hanging up in the tree, so it would be straight until we got here, and then it would be quadratic. Don't let that confuse you. But this one does work in the problem, and it does make sense. We know that this is our number of seconds. We know that this is our number of feet. So after falling for 1.25 seconds, the coconut reaches a height of 0, which we're going to call the ground. So my x-intercept here tells me in 1.25 seconds, the coconut is now at a height of 0, or it is on the ground. All right, the vertex. The vertex of this is 0, 25. You might also notice that the vertex in this problem is also our y-intercept. That's just because there was no initial velocity. But in this problem, again, we read the graph. 0 is my x, which is time in seconds. Y is my height, which is in feet. So at 0 seconds, how high in the air was the coconut? Well, at 0 seconds, or the beginning of it dropping, it was 25 feet above ground. Or coconut started 25 feet above ground. Domain of this function compared to the domain of the problem situation. So again, the domain of the function is always going to be all real numbers. But in context of this problem, at what times is the coconut falling? It's not falling in negative time. We're not going to look at negatives. And after 1.25 seconds, is it still falling? No, it's not falling anymore. So although the domain of the actual graph is all real numbers, the problem situation, the domain is just from 0 until it hits the ground at 1.25. So again, domain of the problem situation is just what x values make sense for this problem. And this problem was the coconut falling, and the coconut only fell from 0 seconds to 1.25 seconds. So those are the x values that make sense. The range, well, we know the range of the actual graph would be y is less than or equal to 25. But if we just say y is less than or equal to negative 25, that means we're looking at negative heights as well. I do agree that 25 feet was the highest the coconut was at, but what's the lowest the coconut was at? Did it go to negative 10? Did it go negative 20? No, the lowest that the coconut went was the ground, which has a height of 0. So the range in context of the problem, right, that's the important part. In context of the problem, the range, the y values, or the height at which the coconut was in the problem, it was as low as 0 feet when it hit the ground, but it was as high as 25 feet when it was still in the tree. So in context of the problem, we're only looking at heights from 0 to 25 feet. All right. In conclusion, one real-life scenario for quadratics is the vertical motion model. This is a vertical motion model. We're probably not going to ask you to write very many equations, if any, using it. But once we graph it, we do expect you to be able to interpret the graph, be able to talk about the vertex, what it means, the x-intercepts, what they mean, and the y-intercept and what it means. Hope you guys are doing great. Have a wonderful day.